All right, thanks, Karthik. Can the guys in the back hear me fine? This thing is working, right? Okay, so hi, my name is Isuru Rajapakse. I'm an Android developer and I work at Motorola Solutions. We make radios and we also make apps for police officers and stuff. But today I'm going to be talking about the design trends that you don't need to apply. I want to give a little bit of context as to where this talk is coming from. It's based on this book. It was released 30 years ago, and it's been a while. And it's based, it talks about, the name of the book is Design Patterns, Elements of Reusable Object-Oriented Software. So it talks about object-oriented software design patterns. It has these three different kinds of design patterns: creational, structural, and behavioral. It's written by 4 people, and that's why you call it Gang of 4. It's written in the context of Smalltalk and C++. So but it's actually widely adopted by Java folks. So that's why I'm talking about it today. I want to emphasize that these design patterns are really just based on a problem domain, meaning that if you don't have the same problems, you don't really need the same solutions. And the context for my talk today is going to be Java. More specifically, though, I'm going to be talking how they sort of translate over when you try to adopt them in Kotlin. So let's get into it. There's 22 patterns to go through. We're not going to go through all of them today. But what we're going to do is we're going to go through each of these pillars and grab one of them and see how we can translate them over Kotlin. We'll start with creational design patterns. Again, there are so many design patterns to go through. There's prototypes, there's singletons, there's factories, abstract factories. And the one that I'm going to be talking about today are the builders. So before I jump on and explain, hey, this is the builder, do that, I'm going to explain why you should do the builder. Here, I have a simple car program. We can take a closer look. I got a car. The car has a number of seats, a door, a couple of flags indicating whether the car is registered and insured, and also maybe a sunroof if you're fancy. Definitely an engine because it's not electric. And we also have a constructor that takes those parameters as arguments to construct the car. And down here, I have a simple program that creates a car object. This is as easy as it gets. Now, at this point, we can ask, hey, what's so bad about this? Why do we need a builder? Well, first, we have to provide all these parameters, all these arguments in the same exact order. Otherwise, it would fail to compile. Now, the second problem is that now we have these flags, and we don't know what these flags are really for. Could be if the car is insured or if the car is registered. Without looking at the declaration side, I have no idea. And it's easy to make mistakes by passing them in the wrong order. And third, let's say if our car sort of changes over time. Now our car has a list of lights that we have to take care of. You could go on and change the constructor's signature, but this would lead that particular use site being incompatible with the previous use sites. So essentially what you've done is that you inherently couple the internal representation to its construction. And this might not be that desirable. All right, quick recap. So without the builder pattern, your constructor requires all the arguments to be passed in the right order, and there's some sort of a use site confusion at you're not sure what flag is what. And third, you're essentially coupling the internal representation to its construction. All right, so how can we apply the builder pattern to solve that problem? All right, so this is the officially prescribed solution from this book. So instead of on top of the car that you already had, now you have to have a car builder. So let's take a look at this car builder. So the car builder has one responsibility to build a car. You can ask it to build, it'll just spit out a car for you. And on top of that, we will have a constructor for the car builder. And at this place, we can enforce all the required parameters for your car. So you can say, hey, if you want to build a car using my car builder, you have to give me an energy. On top of that, we can also use this place to assign all the sensible defaults. So for instance, if you ask my car builder to build a car, I can say, hey, my car will have 4 doors, or however number of doors you have. And you would also have accompanying builder method to set those doors if you want a different number of doors. Maybe you're building a limousine, who knows? Okay, I'll add the 2 flags that we had before, the registered and the insured flag, and the accompanying builder methods for it. And let's see how we can use this at our use site. So with the builder in place, our use site looks slightly different. Instead of a big constructor call, now we have this chain of construction calls and then the final build call. Great. By doing this, we've sort of avoided the use site confusion. Previously, you had no idea what these flags are. Now you do because there's a builder method that you call for it. And more importantly, you sort of decouple the initialization order from its construction order. So you can reorder these functions however you like and still be able to create out of it. Okay, so we managed to solve all the problems we had before. We removed the requirement around the arguments to be passed in that order. Now you can pass in parameters in any order you want. We eliminated the use site confusion. So at the use site, you know what argument is which. And we finally decouple the constructor from its internal representation. Awesome, right? Let's actually ask ourselves, why are we doing all this? Let's take a look at the same example solution we have before. Now, instead of just a car, you have this car builder thing for you to take care of. So instead of 1 type, now we have 2. And on top of that, you have to duplicate all the internal representation you once had into the builder so you can build something out of it. On top of that, if the use site forgets to call one of these set seeds method, and if it's one of the fields that you don't have a default for, it would just crash at compilation time. Sorry, it will crash at runtime, which is worse. So by solving the problems we had before, we've sort of introduced 3 more problems to deal with. So let's see how we can make this a little nicer with Kotlin. So I'm going to rewrite the same exact thing in Kotlin. And when I write the constructor for this class in Kotlin, Kotlin compiler will actually warn you at this point, saying that, hey, this looks like you can move this to the primary constructor. So what I'm going to do is I'm going to do that. And when you do that, it looks like that, which might look weird for the Java folks here. But what I'm doing here is I'm combining both the declaration type and the primary constructor itself into a single declaration. Now, we can actually use the primary constructor itself as the builder. And this is how that looks like. In my main program, I'm going to call the car function constructor. And at this point, you might ask me, hey, isn't this as confusing as the Java example where you don't know what of those 2 labels actually stands for? And you're right, we don't know that. But the solution is quite easy. We can just use Kotlin's label parameters feature to avoid that confusion altogether. And in Kotlin, we also can, as long as the parameters are labeled, you can reorder them in any order you want. It doesn't have to be the same exact order. That way, we also solve the problem of the constructor requiring the arguments in the same order. And this effectively decouples the order of initialization from its representation. Kotlin also lets you do a very nice thing, which other languages doesn't do, which is threading commas. Right? With that, you can also move this thing anywhere you want without worrying about where the last comma is going to be. Okay, so similar to the builder, we still can have sensible default values. So what I'm going to do is I'm going to move the values that I had into the constructor. So when you create a car, it'll come with those defaults. And if you want something else, you still can override that at the use site. Unlike the builder pattern, though, we still have the compile time safety. So if you don't provide the engine, it would fail to compile. And if you don't provide, let's say if you have the list of lights, if you don't have default for that, it will also fail. So for instance, let's say if your car changes its representation over time. Now, similar to the Java example, we can add that extra field. Now, at this point, your car would no longer be backward compatible. Any use sites now would have to manually migrate the declaration sites, but you can help a little bit by assigning a default. This would make it source compatible, not binary compatible. It'll be source compatible. And if you still want a completely different internal representation, what you can do here is to provide a secondary constructor. So here I want to have a secondary representation where you could just pass in a policy and it'll just create a car out of that. And you can actually move that secondary constructor out of the actual class itself, completely decoupling it from everything else. And I call these fake constructors because it looks like a constructor, but it's not. But what this will do is it will completely decouple the internal representation from its construction, which is what build is for. So by just using primary constructor, I managed to solve the problem of additional type. You no longer have that additional constructor type. You no longer need to duplicate all the fields, and you also saved yourself some compile time safety. So when you're writing in Kotlin, you don't actually need to rewrite the car builder classes or any builders for that fact. You can just use the primary constructor with some default sensible values. Okay, so with that, we effectively took a jab at one of the creational patterns. Let's go to some structural patterns and see what we can do. Again, there's too many types to go through. There's facades, there's composite patterns, bridges, flyweights, proxies, decorators. But the one that I want to take a look at today is the adapter pattern. So we'll do the same thing. We'll ask ourselves why we are doing adapters. To illustrate that, imagine we have these 4 classes. So here we have a road class which has some associated distance in it. And here we have a library class called the vehicle, which has some mileage. And when you create this car, it'll come with 0 mileage. And every time you ask the vehicle to travel over a given road, we'll add to that mileage. For the sake of the argument, just assume this is a library class and you can't edit that. This will be relevant in a bit later. Down in the sample program, I'm going to create a road. I'm going to create a vehicle, put the car and ask the car to go over the road. And this works fine. But imagine if you had a separate thing that you want to travel over. Let's say you want to make the vehicle travel over a canal. At this point, since you can't change the vehicle, you can't ask the vehicle to travel over the canal. It would just fail to compile. And this is the problem the adapter pattern is meant for. So with the adapter pattern, the 2 interfaces are compatible and they wouldn't be able to work with each other. So what does this book tell you to do to solve such kind of problems? According to the adapter pattern, instead of on top of all the classes we had before, now we have to have an adapter. In this case, I've named my adapter the ferry, which thematically makes sense, I guess. We'll take the car over the canal. In the adapter pattern, I'll keep a reference to the thing I want to adapt, in this case, the vehicle. And when you construct the adapter, I'm going to pass a reference of that. You ask the ferry to travel, what it'll do is I'll create an imaginary road and ask the road to travel over the imaginary road. Ask the vehicle to travel over the imaginary. All right, so on the use side, what we're going to do is we're going to create a ferry. I'm going to create my adapter, and then finally ask my adapter to travel over the canal. So with that, we've successfully allowed these 2 incompatible interfaces to talk together. And that's what we did with the adapter pattern. We were able to convert one interface to a different interface that it expects. All right, so let's take a step back and ask ourselves, why are we doing this? What's so wrong about this approach? Well, the first thing I think is that we have this additional wrapper class, which is the ferry class. It's something that we didn't have before, but now we have to keep track of. But I think the most egregious thing here is the fact that previously we had direction, so we could have just simply asked the car or the vehicle to travel over the given road. But this new wrapper, we've lost that direction and we come up with something indirect. Instead of asking the vehicle to travel over the canal, now we have to put that in a ferry and ask the ferry to travel over the canal, which is indirection. So again, in order to solve that problem, we added 2 more problems on top of that. So let's see how Kotlin can help here. So I'm going to rewrite the same exact program in Kotlin. This is identical to the Java example. But instead of creating an adapter class, I'm just going to create what you call an extension function. If you haven't seen one of these before, I'll explain what this does. We're essentially extending any arbitrary type. In Kotlin, it lets you do that, and you call them extension functions. They come with something called the receiver, or the primary receiver in this case. With the receiver in place, you can extend any type if you want, even the platform types. I'm going to invite the extension function and do the same thing as I did before in the ferry. And this extension function now effectively works as my adapter. When I want to use my adapter, all I have to do is so I'm going to rewrite the same exact program in Kotlin. And in order to use the adapter, I can just call it like you typically do if you are calling a library function. Just like how you would ask the vehicle to travel over the road. These 2 function signatures, although they look very similar, they are actually calling 2 different things. Again, we are still not introducing indirection. Everything is direct. Okay, so just by avoiding that extra adapter class, we've avoided adding extra type abstraction. And we also maintain the directionality, which is making it more readable. Yeah, so when you're writing classes in Kotlin, you wouldn't actually need an adapter. You can just, most of the time, pretty sure all of the time, you can just write an extension function. So in Kotlin, no adapter is needed, just write extension functions. Okay, with that, I took a jab at one of the structural patterns. Now there's one more thing to go. Let's talk about behavioral patterns. Again, there's too many to count, even to remember. There's chain of responsibility. I'm not going to count all of them, but the one I'm going to talk about today is the state pattern. To explain how this works, I'm going to go back to the chemistry lab and take a look at how I'm going to model a simple sample program with states of matter, which is water, liquid, solid, and gas. There are specific transitions that these things can go through. Like for instance, liquid can frozen. The liquid can be frozen, and the solids, the ice can actually sublimate back to like an air, a gaseous state, and gas can condense back to liquid. So we're going to model that in a simple Java program, and that's, oh man, this animation is so slow. It looks fast on my machine. But what we have is a simple sample program. On top, we have a state machine or enum that represents 3 different states. And here we have an abstract matter class, which I can perform different transitions on. So I can ask the matter to sublime, melt, whatever. And I also have a concrete one of these abstract classes called water, which you can ask to heat up and do all that stuff. So for instance, when you ask water to heat up, if it's already in the gaseous form, it wouldn't do anything. If it's in the liquid form, it might evaporate. And if it's in the solid state, it might melt. When you ask water to cool down, if it's in the solid state, again, I don't think you can cool down ice further, maybe like down to 0 Kelvin. If it's in the liquid state, it might freeze. And if it's in the gaseous state, it might condense. On top of all that, there are also specific transitions. For instance, you can ask water to evaporate, but if the water isn't in the right state, you'll throw an illegal state exception, which is quite nice because you're talking about state. But if it's in the right state, you'll convert it to the right state, convert it to the next state. All right, so we have that all set up. Setting up the main program is pretty simple too. We just create a bottle of water, and then ask the water to start off in liquid format, as liquid state. And when you ask it to cool down, it'll go into solid. And then you can melt it, I guess, which will turn it back into liquid. And finally, it will heat it up, which will make it a gas. And if you ask the puddle to condense at this point, since it's not in the liquid state, it should be drying at this point. Okay, so that's the sample program. Let's take a closer look over here. Now, if you look at this piece of code here, you'll see that all the state, all the logic that was associated with the given state, they're no longer in the same place. They are sort of fragmented between these two functions. And if you expand all the other functions, you will also see the same. And I think that's the problem the state pattern is fundamentally solving. It's turning all this fragmented code into, they do not try to co-locate all that code into a single place. So you can see that the solid state, that those two function calls are in two different places. The same thing goes for all the other states. So without the state pattern, oh man, the animation is so slow. You have fragmented logic, and on top of that, it really makes it harder to read to reason about these different states. All right, so let's see what the gang of four describe here. According to gang of four, we now have a state class. So before, what we're going to do is we're going to move all the logic that we had in the water class into the state class. So previously we had the enum value, but now we have a whole class. Here I'm going to have the arbitrary heat up and cool down methods. And I'm going to subclass this, and I'm going to introduce three other classes, solids. And in this case, if you ask solids to heat up, it'll just melt. But if you ask it to cool, it won't do anything. And similar logic from the previous code or program also comes through. For instance, ice or liquid, when you ask it to heat up, it might evaporate. If you ask it to cool down, it's going to freeze. Okay, so water, now what should water do? What all it needs to do is to keep a reference to the state. And when you ask specific state transitions, it's simply going to delegate that out of that class. So where are we going to put the evaporation function? We could, for now, let's just throw it in the abstract class. And that's how that looks like. Okay, so with the state pattern, this is what you get. If I bring in the previous example where you had no state pattern, and now you have state pattern, and if I color code this, you'll see that previously our logic was fragmented. So, right. But now our logic is co-located. They are located together. And that's the whole reason why we should have the state pattern. It get rid of the fragmented logic and co-locate all the logic together. And it makes it easier to read and reason about these states. Okay. Why? Why do we need to do this? Let's try to just take a step in and see what's wrong with this. If you look at the water class, all it's actually doing is delegation. If you can look past all this boilerplate, another issue you might run into is the fact that with this state pattern, you can easily run into states where you can ask the water to heat up when it can't. So you can technically run into invalid state transitions. If you look at the actual implementation, it will throw at runtime. So we're kind of losing, here we're kind of losing all this compile time safety that we had. So we are introducing boilerplate, but even if you can look past that, our state machine can run into invalid state transitions. So how can we solve that with Kotlin? Okay, so let's introduce an see the interface called matter, and I'm going to subclass that into liquid and solid and gaseous states. And in this interface, what I'm going to do is I'm going to create concrete types called ice, water, and vapor, which are the actual concrete types given the abstract interfaces. And in the serial interface, instead of putting all these state transition functions up here, I'm going to actually, one thing I'm going to do differently here is that I'm going to, instead of changing an internal state, I'm just going to simply return an immutable state. That slight change will make it more evident what we're doing, and we're eliminating having to contain an internal state. You'll see in a bit later what's that important. In the solid class, so previously we had these melt and sublime functions in the abstract interface. But what I'm going to do is I'm going to move it down to more specific scope interface. So I can only ask ice to cool down. You can only ask ice to melt. For instance, in the case of liquid, since the evaporation functions are only on the liquid interface, you can't actually ask ice or solid things to melt. So we're essentially implementing a scope method here. And the same goes for ice. With ice, you can either ask them to melt, sublime. When you ask ice to heat up, which will melt. If you ask ice to cool down, it wouldn't do anything. So let's bring back the previous example. You can see that all the code we had for that given state are still co-located. So previously we had fragmented logic. Now we have co-located logic. Okay. And we all did all that without introducing extra boilerplate. If you want to see how the user looks like, this is how that looks like. Instead of having a single reference and performing mutations on it, what I'm going to do is I'm going to have a single reference and perform mutations on this. And with this approach, since we are passing and chaining down the states from one function to the other, we are also able to retain the type information and enforce invalidate any invalid state transitions. For instance, if I ask gas to evaporate, you wouldn't even be able to compile this down because gases can't evaporate. So we are keeping some compile time safety. So, but just by using a seal class and sort of taking on immutability, you sort of get rid of all the boilerplate we had. And we also eliminated any invalid calls to invalid state transitions. Okay, so with Kotlin, you don't really need to implement state machines, state pattern. You can implement the state machines with just sealed interfaces and some scoping and also embracing immutable state. And with that, I took a jab at one of behavioral patterns. Now, going to the epilogue, again, there are so many other patterns to go through. Like, I don't have the time to go through all of them, but we went through the adapter, we went through builders, and then finally state machines. I have just 3 principles. One is case, keep it simple, stupid. If you don't want to introduce extra stuff, don't do that. It's great advice, just hurts my feelings every time. And second advice, keep it concise. There's a nice quote I like to quote here, which is, if I had more time, I would have written a shorter letter. Adding stuff into a program is easy to do, but it actually makes it harder to read in the long run. So if you have the time, make it concise. And finally, let the tooling do the work. If a language can support extra concepts like design patterns or things like singletons, you don't have to write them. You can just use the language constructs for that. So if you have this, it's not just specific to Kotlin. If you language of your choice, if that lets you do these patterns from the get-go, just use the tools. Because you don't want to give the responsibility to the dev. You'd rather give that responsibility to the tool. Again, I talked about patterns a long time ago. You can see a talk about visitor pattern over here. This is from 2 years ago. And you can also check this channel out. And Dave, if you're watching this online, thanks for reviewing my talk last minute. And I'm also going to give a shout out to Alexei, who wrote the book on the design patterns. And thank you. You can see all the book.